So in this problem, we're given a situation that looks like this. We have two masses, both of equal mass m, connected by a string across a frictionless massless pulley, and both of them lie on a triangle, one of them at an angle theta, and the other one at an angle phi. So the first thing we're asked to do is draw an isolation diagram for each mass. So the first mass, which I'm going to label mass number 1, this is going to be mass number 2. Mass number 1 has a force mg pulling it downwards, the normal force pushing it up away from the triangle, a tension force from the string pulling it back up the edge of the triangle, and the friction force pulling it along with the tension. We're going to define downwards to be positive x and upwards to be positive y. And note that the friction force is going in this direction because we're given that theta is larger than phi. We're actually given exact values for theta and phi, but it's going to be a little bit nicer to solve things in terms of these variables. So because theta is larger than phi, the force of gravity pulling it down is going to be greater than the force of gravity pulling this along this slope, which means that ultimately, if the two were going to move, they would move in this direction, which means that the force of static friction has to oppose that. Now for the second mass, we still have the force of gravity pulling it down, but the normal force points in the other direction now. We also have the tension force pulling it up, as we did for the other block. And now we have the force of friction opposing the tension force. And that's because if this block were to fall, this block would have to rise, which means that that's the motion that this force has to oppose. So now what we're going to do is we're going to do a sum of the forces for each block. First, for block 1, we get m1 times a1 equals, and it's going to be 0 because we're looking for what the coefficient of static friction is going to be if the blocks do not move. So the minimum coefficient of static friction so that the blocks will not slide up or down the track. So for block number 1, this is going to be mg times the sine of theta, because if this angle right here is theta, then that means that this angle right here also has to be theta. So we get mg sine theta minus the force of friction minus the tension force. And the force of friction is just going to be mu sub s times the normal force, which is mg cosine theta. And then we still have the tension force. For block number 2, we have m2, a2, but they're exactly the same, so I'm just going to write ma because they have the same mass, and they have to have the same acceleration because they are connected by a stretchless string. And this is also going to be 0. And this time it's going to be pointing in that direction because upwards is along the slope is positive x, and upwards away from the slope is positive y. I should have drawn that before. This was a wrong isolation diagram because it didn't have an axis. So this is going to be 0. This is going to be tension minus force of friction minus mg sine theta. And now again we have the force of friction that we can plug in for. We have tension minus mg sine theta minus mu k, or mu sub s, mg, and this is, this is phi, because this is for this angle. So mg sine phi minus mu sub s, mg cosine phi. And so now, since we have both of these equations, both of these accelerations are 0, which means that these tension forces, which have to be the same because the string is massless, so the tension is the same at both ends, these tension forces have to cancel out these other forces. So this tells us that the tension is equal to mg sine theta minus mu sub s mg cosine theta, but it is also equal to mg sine phi plus mu sub s mg cosine phi. Notice that these two terms have the same sign, while these two have opposite signs. And that's because on one hand the force of friction is helping tension, and on the other hand the force of friction is opposing tension. So now we can set these two equal to each other. We're going to cancel out all of the mg terms because they don't matter to us. And so we get sine theta minus mu sub s cosine theta is equal to sine phi plus mu sub s cosine phi. And we can now rearrange this to get mu sub s on the same side. And we get mu sub s cosine phi plus mu sub s cosine theta is equal to sine theta minus sine phi. And now we can divide this out, and we get mu sub s is equal to sine theta minus sine phi over cosine theta plus cosine phi. And now we can plug in the values that we're given. We know that theta is equal to pi over 3, and we know that phi is equal to pi over 6. And this tells us that since we know sine theta and cosine phi are both the square root of 3 over 2, and sine phi and cosine theta are both 1 over 2, this gives us mu sub s is equal to root 3 over 2 minus 1 over 2 divided by root 3 over 2 plus 1 over 2, and we can cancel out all of those two denominators to give us mu sub s is equal to root 3 minus 1 over root 3 plus 1. And that is our final answer. This is the minimum coefficient of static friction for which these two blocks will not slip.